Please welcome Dr. Anne-Marie Sastry.
Can you do me a favor? Take out your cell phone. I'm not going to make you turn it off. The organizers want you to turn it off. Take out your cell phone. You're a superhero. Energy storage reimagines human beings as superheroes. With batteries, we can talk to people on the other side of the planet. We can check our email. We can, in electric vehicles, drive aphysical distances. Batteries store energy when the sun's not shining and the wind's not blowing. Batteries reimagine human existence as a collection of superheroes. This is why I've worked in batteries so long. They're in just about everything. Cell phones, power tools, cameras, laptops, electric vehicles. They're myriad all over the planet. And inside your cell phone is a lithium-ion battery. Now that came from a long line of progenitors. It came from, at the turn of the last century, an innovation called the nickel-cadmium battery. And that became ubiquitous, and then the metal hydride battery became ubiquitous, and now everybody has on board a lithium battery. Inside that battery, you might think it's just a bunch of solid pieces of stuff, but actually it's a lot more complicated than that. Inside the battery that you have in your smartphone today are an agglomeration of particles packed together and glued together and filled with liquid. In fact, the only liquid or gel in your phone today is in your battery. The top picture are SEMs of what typical cathode materials are, and the bottom pictures are SEMs of what typical separator materials are. That's a lot of complexity. And engineering and improving that battery cell so that you can talk, move, store energy, and become a superhero is an interesting problem. Now, first, a little bit on how a battery works. And it's really simple. One half of the battery cell basically has to move to the other half of the battery cell and back again. There aren't too many engineering devices like that. It also has to still stay small, so the energy density is high. So you can talk all day or drive hundreds of miles in your electric vehicle. That's called energy density. During discharge, all of the lithium ions on the anode side of the battery move to the cathode, and that creates an electrical current. On charge, the reverse happens. So an electrical current is applied to the battery cell, and all of the lithium ions are forced back into the original configuration. So pretty simple, right? Except that that's not a solid piece. As you saw in the SEM, it's made up of packed particles that are filled with liquid. And the evolution of the battery cell to today's electrochemistries and today's configurations, which have metastasized globally, all battery cells are essentially made the same way, was through a series of problems and solutions of the engineering challenges. First, low diffusivity. You saw how the lithium ions have to move from one side of the battery to the other. Well, it's easier if they're in a liquid. That's diffusion. And so that's why liquids or gels are used inside batteries. If you use a liquid or a gel, you can't use a solid, right? So the material is made out of particles that are pressed together to make it porous, right? Another issue with your battery cells, capacity fade. When you first get your smartphone, it charges up nicely and you can talk for a few hours, right? What happens 3 months later? Not as good, right? That's called capacity fade. And it was discovered that formation of a layer over those particles actually slowed down that capacity fade and improved that. So that was another engineering step. Low electrical conductivity was also an issue because you have to get the electrons out of the battery to drive an electrical circuit, right? So the solution to that globally has been fill it with little bits of carbon, fill it with carbon materials, and then glue it together in a matrix. So that's how you get from a solid layer, which should be pretty simple, to something really complex. When we were thinking about battery cells, I was a professor at the University of Michigan, and my teams and I worked on this problem for about 17 years. And we were thinking about this for a long period of time in terms of how can we add, subtract, multiply, divide materials to make the perfect set of complex materials. But an overarching question we developed a few years ago was, is there a solution that embodies simplicity? instead of re-engineering all of these bits and pieces of materials inside the battery, could we do something like this? Simple. Solid layers, right? Current collector, cathode, electrolyte, anode, current collector. A stack of solid materials that would function beautifully. Would have the advantage of not having all that other stuff that you want in a battery. You don't want to pay to carry around conductive additives. You don't need a liquid that doesn't store any energy. You want to reduce and redact the material down to just that which stores energy. And if you do that, mathematically, you can get the highest energy density of any architecture of device. There's a challenge. Everything needs to be able to get to the right place. So you saw how those lithium ions have to move from one side or another. It has to look like this. The lithium ions have to get all the way to the back of the cathode. That means you have to have sufficient diffusivity in a solid material to do that. Fairly tricky. So here's what we did. We built at Sakti3 some finite element codes, which are numerical codes which would allow us to do massively recursive calculations on what those thicknesses and what those materials would have to be in order to perfectly intercalate lithium in perfectly stoichiometric proportions. All the lithium is over here. Now you see it. Now you don't. And we projected that if we could get that done in 2011, we could double the talk time on your phone and the range in your electric vehicle. So this is what we predicted. We predicted 1,170 watt-hour per liter in 2011. Pretty good, right? Then we had to go make it. So we started to think about how could you make these films? We looked at stuff like this. It's pretty expensive. You'd probably crack out about one battery a year with that. And at the tool cost of $10 million, that's not very economical. Basically, nobody could really have a better battery if we went and did that. We might be able to write a nice paper with it, but we decided not to do that. Instead, we went back to work. So we wrote more codes. We started to calculate piece by piece by piece in a factory what would the pieces have to be to process the material, and working backward from that, selected the platform to design on. And we came up with this. Cheap film metallizers. The kinds of vacuum equipment that makes cheap stuff. Tape, food packaging, bread wrappers, like that. So then the riddle was, how do we coax a battery cell out of a machine that makes cheap stuff like that that has double the energy density of today's technology? So we experimented. For 3 years, we persisted. We bought 5 different pieces of equipment on eBay. We brought in people to the company from 5 different countries. We did massive designs of experiments. We did massive recursions and calculations and experiments. We measured properties in the lab, ran back to the design area, and did more simulations, back and forth, back and forth, back and forth. And in 2014, we found we were pretty much on target. So we had predicted 1,170 watt-hour per liter. And this year, we announced that we had achieved over 1,100 watt-hour per liter, specifically 1,162 watt-hour per liter. We still left 8 watt-hour per liter on the table. We don't know where that is. We're going to go find that next. But this is where we're at. OK. So what's next? Well, meanwhile, the incumbent technology has kind of asymptoted. It's not really getting much better in terms of energy density. If you look at what's happened in the last 20 years or so, it's about tripled. But we've kind of hit the wall. And you can kind of understand why when you see the complexity of the material. We've demonstrated that number up there, which is almost off the chart, right? And so we believe that the solid-state platform will be another design platform. So Sakti3 will be working very hard in the next couple of years to commercialize that technology so all of you can have it. We think that will mean better devices, electric vehicles that everybody can afford, and storage of renewable energy, and new stuff too. There are lots of things that we can imagine, but we can't execute without better batteries. Electric aircraft, better robots, more electric vehicles, and smart grids finally. So I appreciate the opportunity to be here with you this morning, and please root for us as we go towards commercialization.